Hey, Bob, can you unmute?
I'm so sorry, Lisa. Okay, so this part got omitted. All right. Can you hear me now?
Yes, I can hear you now.
Sorry about that. Okay. All right, so let's get back to this. Epsilon T equal to 0.005. Sorry, bigger than 0.05 tension control. That means what? Yield, fine, great. But more directly, that means what? Phi equal to what? 0.9. There you go. So that is the strength reduction factor, phi equal to 0.9. Okay. Okay, so with that, I can say that nice, so they got everything, right? So Mn, moment capacity, equal to As Fy multiplied by ds or dt. ds or dt? ds, right? ds. Lucky for me, it's the same thing for this case, but be careful. It is ds right here. ASFI 2-inch square, 60 ks, 120 kips of tension force, multiply ds 21.5 inch, minus a. What is my a? A is 2.94 and divided by 2. And I have here Mn equal to a 200.3 kip foot. So my design strength, phi Mn equal to 0.9 multiplied by 200.3 kip foot, roughly equal to 180 kip foot. This one is my design strength. So is this okay? Sufficient? Yes. Why? Bigger than mu. That is 145 kip foot. Okay, don't forget what we're doing here. Okay. All right. Suppose they were done. Suppose they were done. Okay. But if you take this and go on a job site and tell them this is my moment capacity, this is my area of steel, they will not let you do it. Why? They will ask you one more thing I haven't mentioned about. It is so-called a minimum reinforcement area or minimum area of reinforcement. Now, this concept we haven't talked about, and I'm going to talk about today. Okay. Now, you've done the homework, right? You've done the homework. And there was a question asking about a capacity of a section without any reinforcement in it, right? What did you say? I just mentioned it's a cracking moment, right? It is a cracking moment, right? And what we said about beginning of every lecture, what did we say? Concrete is good for what? Compression. So it is not good for tension. So the cracking moment for a good 12-inch, 24-inch of section is about 40 or 30 kip foot. Is that right? What we have done with only two number 9 bars, 180 kip foot, right? So that's a big difference. What does it mean? It means that if you have a concrete beam that has no reinforcement in it, it is so bad you cannot even lift it with a crane. Right? Right? Remember beginning of lecture, if I don't have any reinforcement, I have a section of pole. If you fabricate pole at your home for your fences, at least put some steel meshes in it, right? Because if it doesn't have steel, it will crack. Once it cracks, it's worthless. Right, so that was the problem. So back in the 1950s, and this is in our textbook, an airplane hangar, people fabricated a cantilever beam without any reinforcement in it, okay? And that thing just cracked, okay? And fatigue loading, whatever loading, caused that beam to fail. And afterwards, the engineer says, look, we got to have some rules. We have to put some reinforcement in it, isn't it? Have to put some reinforcement in it. So even if there's no load required to be exerted on the section will hold. So ACI says there's a minimum requirement. I can't remember the section number. I'll add it on later. Let me see if I have it here. Okay, but I remember the equation. ACI says the minimum area of steel or reinforcement need to put in has to be this equation, and that has to be the larger of 2. First equation, 3 square root f prime c divided by fy, and this is like a factor multiplied by bw ds. Okay, the second is 200 divided by fy multiplied by bw ds. Okay. All right. So let's take a look at the equation, right? Let's start from something simple. What is BW? This is called the web width. What is called web width, Bob? Meaning if I have a rectangular section, this BW is just my width. But if I have an T-beam, my horrible drawing here, let me clear it up. If I have a T-beam, my BW is then the width of the web right here. If I have an I-beam, it is also the width in the middle section right here. So BW meaning is the minimum width of the section you're designing for. Okay. Now DS, you know it, it's basically the depth of the bars. So not DT, but DS. So if I have so many bars, that is the distance from the top to the centroid of the bars. That is easy, right? Now, B is the width. Depth is another dimension. When they multiply together, it gives you what? What kind of unit I have? Inch multiplied by inch gives me what? Square, right? So that is an area, isn't it? Area, right? Look at what we're looking for. Minimum area, right? So essentially, is this factor in front of it multiply this base area, right? So this is like the percentage of steel you needed for the section, isn't it? So that's what the factor in front of it represents. Let's take a look at the factor. At the bottom here, what does it say? Fy. What is Fy? What is Fy, folks? Yield strength, right? For grade 60, what I have here, 60 KSI, right? So let's just start working on it. So I know, look, what I have here provided is AS provided here is 2 number 9 bars, so 2 inch squared, right? So AS mean in this case, I'm just start using the equation equal to larger of these two, right? So plug in the number in. So here I have BW ds. Here I have 3 square root F prime C Fy. So BW ds, BW is 12 inch. What is my ds here? Come on. Come on. What is ds? 21.5 inch. And get ready, right? Bring your calculator out because I didn't calculate this number here, okay? Bring your calculator out. So at the bottom here, I'm supposed to have 60 KSI, right? So let me just say 60 KSI. Top there, I have 3 and square root of F prime C, and I'm going to put 4 KSI there. Okay. Can I do that? Can I do that? Ooh, I'm trapping you again, right? Bob is trapping me again. What is playing here now? What is playing here now? I'm playing the problem with the unit. I'm showing you there's a square root. And have you seen the square root of prime C before? Have you seen this before? Somewhere, right, in your life, you've seen this fellow before, right? This dark Vita, right, is hidden in the 7.5 square root of prime C, right? Remember what we said about 7.5 square root of prime C. What's the unit in F prime C? PSI or KSI? PSI. Okay, so that's where I'm playing you guys at. So here, cannot use KSI. Instead, you use 4,000 in the square root sign. Okay. Now, at top, I use PSI, and the bottom, I better use PSI to match it. So that is the correct unit. Okay. All right. So now with that, please give me a number here. Okay. Please calculate it and give me a number here. So 3 square root of 4,000 divided by 60,000 and multiply 12 and multiply 21.5 to make it easier for you. You don't have to change this, but I can do this. Okay. What do you have? Come on, come on. 0.816. 0.816. Let's just call it 0.82 inch. All right. Anybody confirm?
Yes.
All right, good deal. So that's what we have, 0.82 inch. Okay, so let's take a look at another one. The other one is 200 divided by Fy and BW ds. Now 200, say there, Fy is in terms of 60, again, 1,000 PSI, multiply 12, multiply 21.5. And what do you have here, folks? What do you have here? Come on. What do you have here? Move your finger. Let's do it. 200 divided by 60,000, multiply 12, multiply 21.5. What do you have? 0.86 inch squared. Okay, 0.86 inch squared. Anybody confirm? All right, good. So now these are the two equations. These are two numbers. Which one would you pick? The bottom one, right? Why is that? This is what? The larger one, right? You may laugh, Bob. I know who's bigger, who's small. Trust me, in exam, you don't remember them anymore, okay? So be careful, okay? Remember this, okay? Practice in your heart. Always the bigger one. So in exam, right away, pick the larger one, okay? So that is 0.86 inch squared. But does that mean, are we okay? Are we okay? Why? Some of you nod your heads. Why? Because what? How much we provided? There you go. So we are okay. So this is called reinforcement check. Minimum area reinforcement. That happens in your homework number 2, problem number 1. End of it. End of it. Okay. All right. I only have 2 students ask me the question, so I start worried. Okay. You should have asked me the question yesterday. Okay. Anyway, so this is how we check the reinforcement. Okay. Now, before I finish this section, let's take a look at these 2 equations again quickly. Does these 2 equations make any sense to you in terms of theory, mathematics? How do you trust these 2 equations? Well, I don't care, Bob. ACI says so. How can you trust ACI? You don't even trust your parents sometimes, right? They trick you all the time. You don't trust me sometimes, right? How can you trust ACI? In another way, how do we know? Where do we get these equations from? Have you asked yourself? Probably not, right? So these equations, right? Let me tell you, this is called empirical equations, okay? If you have a doubt, go take a look at your textbook and try to make sense of it in your head, then you remember. This is called empirical equations. Okay, this is probably the first time you are in contact with empirical equations. Apart from that 7.5 square root f prime c thing, this is the first time you encounter with this empirical equations in reinforced concrete design. So what does the word empirical mean? Anybody? Bob, it's not literature class. I don't care, right? English is probably not as good as mine. Why are you asking this? Yeah, I'm asking you. What does the word empirical mean? Anybody? Experimentation, right? So doesn't, in the simple layman term that Bob can understand is what? Trial and error, trial and error, right? That's what it is. So back in the days, it is not that we don't know mathematics or apply mathematical models, because we civil engineer like numbers. We casted thousands and thousands of beams, then did a regression analysis on them and derived equations from fitting the experimental data. And that's how we got them. And that's how we're using them. And you are actually doing the same thing in this day and age, in this era. And the new name for this trial and error of fitting analysis is called what? Machine learning. Intelligence, artificial intelligence, right? That is the same thing. So civil engineer has been doing that in the past 70 years. Okay, get it? When something is too complex, fit equations and trying to use it. So empirical experience, that is learning, training, same thing. Understand? All right. So you know that we are actually the pioneers before the computer science guys. Okay. All right. So that's that. Nice, right? And then we check this reinforcement. Add one more step, right? Analysis is step 6. So checking the minimum reinforcement area, step 7. So let me just add here, step 7, check AS mean. Okay, check AS mean. All right, so now we're back at a question again. We're not done yet, right? We need to take a look at the section and see, I have this section, right? And this is what? B equal to 12 inch. Height is 24 inch. And I got 2 bars nicely sitting right here, 2 number 9 bars right here. And they're sitting at a depth of 21.5 inch. Are we done? Not yet. I'm gonna ask you a question. Can I fit 2 number 9 bars in the beam? Can I do that? Yes, yes. How do you know for sure? Textbook chart. Which table are we using? Table A5. There you go. So from table A5, I find out B minimum was 2 number 9 bars and everything is what? 8 inch. Okay, 8 inch. Okay. If you don't remember how to get this, take a look at your textbook. I will upload table A5 in case you didn't buy it, okay? You will have it on Canvas anyway, okay? I'll upload it. But check your table A5, and this is 8-inch, okay? What if I want to be mean? Bob is always mean, okay? I want to make it harder in the exam, right? So you understand. I say calculate this. Calculate this, right? Calculate B minimum. How are we going to calculate B minimum? How are you going to do that? First of all, do you have enough information here? Let's think of it, right? What do we learn about B minimum? That's called bar detailing, right? Detailing, right? In that lecture, which is 2 lectures ago, I draw the drawing there, remember? And how do I draw a drawing? I start from a corner section, right? And there's something there. Remember something there. What is called the curved thing there, right? What do you call this thing? Stirrups, right? Stirrups, right? So do you know the stirrup here? You don't, right? So when you don't know, you assume number 3 or number 4 to start with. Okay? You assume number 3 or number 4. So just have to specify. Just have to specify yourself. Okay, so let's go with number 3 bars, right? I'm going to put 2 bars here. So first thing first, I need to find the distance between the edge of the concrete to the stirrups and to the gap and to the center of the edge of the bars. Do you have to go there so much work? Yes, we have to. That's our job. Okay, that's our job. All right. So how much of a concrete cover we need to have? How much of concrete cover we need to have? Anyone? Anyone? 1.5 inches. Why is that? Because I said so, right? Do you trust me? Not so much. I trust ACI though, right? Better than you, right? So ACI says there are 2 tables you can use for this. I'm going to show you the 2 tables, okay? Give me 1 second right here. Okay, so ACI have 2 tables. All right, let me open it up. I think it's in my Dropbox folder right here. Okay, where is it? Teaching takes a little bit of time. Let me see where we're at. 21.4, 757. Yeah, let's go with spring. There. Tables. Where are my tables? Okay. There you go. And I'm going to share that with you guys. You can see it. No, anything? Oh, slow, sorry. It's just slow. Come on, come on, come on. Yeah, okay, do you see it? Okay, it's called table 20.5.1.3.1. Yep, very, very long number. 20.5.1.3.1. It's called specify concrete cover for cast in place, non-pre-stressed concrete members. Cast in place, you know cast in place, right? What does cast in place mean? You pour it there, right there, right? What does non-pre-stressed mean? Have you seen the pre-stressed concrete before? I bet you did. Oh, I bet you have. You just didn't know. Okay, let me turn to another question. Have you ever parked in a parking garage before? You did, right? Go to movie theaters, shopping malls, right? You went there, right? We notice one thing, the parking lot floor is always what? Bouncy, right? We drive on it, it's kind of bouncing, right? It's not so stable, isn't it? Have I ever asked you a question, why is it? No, you just get used to it. You thought it's your shocker, right? You thought it's your car, right? But it's not your car, it's the slab. It's actually bouncing. Next time, when you jump out of the car, if you're like me, 200 pounds plus, jump on it. Really, jump on it. See what you have. The floor will bounce. Why is that? Because the floor is so thin, isn't it? So thin, right? Next time, take a look at the top, right? The concrete floor in the parking lot is so thin, right? Why it is so thin? Because it is being pre-stressed. What is pre-stress? What is pre-stress? You stretch it. Yeah, you stretch it a little bit, right? And then you pour concrete, right? Holding the force and you pour concrete. Once the concrete is poured, hardened, you cut it off and the tension force just go back and the whole beam camber it up. Camber it up, go up, right? Have a pre-deflection. So it's more stiffer than the same section area that being non-pre-stressed. Okay, so we actually use pre-stress a lot. Next time, go take a look at it. Go take a look at it. Okay, so in this table, it says non-pre-stressed member is what we're dealing in this class, non-pre-stressed. Okay, if I got intrigued, sign up for a pre-stressed class next semester with Dr. Meyer. Okay, he's an expert in pre-stressed concrete. Okay, so now this table is strictly for non-pre-stressed for our purpose. All right, now you have the table, right? Let's take a look at the table. The left is called concrete exposure. Middle is called member, reinforcement, specific concrete cover. Let me tell you, if I say this beam is sitting at the corner of the outside wall of BCH, which concrete cover am I talking about here? Which concrete exposure I'm talking about here? Which one? Is the first one cast against permanently in contact with ground? Is this one? Exposed to weather or in contact with ground? This one? Not exposed to weather in contact with ground? Or this one? What does all these mean, right? We're civil engineer, right? These are literature, right? What does all this mean, right? So first thing, what do you mean by cast against and permanently in contact with ground? It means that the water from ground can seep in, isn't it? It means that this thing is in contact with water in the ground. Is that right? So that's what this means. So first thing, we'll be in contact with moistures. Second thing, exposed to weather in contact or in contact with ground. What do you mean exposed weather? Is inside or outside? Outside. So this is called exterior. This is called exterior. So let me write down something on it, right? I don't know if I can write that, but you can write down, right? First one is called in contact with moisture. Please write it down, okay? Just put a table there and say that this is in contact with moisture, okay? First one, in contact with moisture, okay? Second is called exterior, right? Exposed to weather or in contact with ground. Last one, not exposed to weather or in contact with ground means interior, interior, interior. Okay, so if I say the beam is at the corner of BCH on exterior wall, which situation am I in? Number two, right? So in number two, and this is a beam, right? Member means this beam, right? Yes, question? Oh, I didn't write anything. My pen doesn't work. I'm just asking to make notes on it. But do you see this table right here? Yeah. No, I cannot write anything. This is my Dropbox, sorry. Okay, I just want you to take a look, right? So member is a beam or column? Beam or column? Beam, right? And doesn't matter? No, all members, right? So second box, right? Second box, all right here, right? All. And then go on. What kind of bars we have here? Number what? Number what? Number 9 bars, right? So which way? Number 6 through number 18, right? So we're in this category. So go here, we're in this category, right? So what concrete cover we're talking about? What is it? 2-inch squared. Clear? All right. Okay. This is the concrete cover. Now, problem. You talk about concrete cover, Bob, and now it's 2-inch squared. Question is this concrete cover from surface to center or clear cover? Clear cover. So this means I need more space in my section. Oops, cannot do the table A5 anymore. Cannot trust table A5. Why? Table A5 is for what? Interior beams, interior non-exposed to weather. Okay, so that is the difference. Okay, normally I don't say anything. You can assume it's interior, go with table A5. But if I said specifically, it is outside the wall, BCH, and exposed to weather, exterior, you have to use this concrete cover and recalculate your beam width. Okay, all right, so it's not that simple, isn't it? It's not that simple. All right, let's get back. A bit difficult. Yes, here, this is where we're at. All right, so now let's just say that for this case, I say it is exposed to weather. Okay, or I will tell you is exterior that means you cannot go to table A5 anymore. Okay, cannot go to table A5 anymore. Instead, you go with the table 20.5.1.3.1, right? Remember that table, okay? Remember that table. Don't remember, go back, take a look at this 20.5.1, something like that, right? And you find that table, okay? And there's only the first table, not the second one, okay? All right, so with that table, I said this is 2-inch. Okay, and number 3 bar, what is the diameter of number 3 bars, folks? 3/8. Okay, and I need a gap between the edge of the stirrups to the side of the bar. What is this right here? 2, what is it? 2 ds. What is ds? 3/8. Okay, this ds is not depth, okay, is the diameter of the stirrup. So this is 2/3. Okay, and I have half of the bar side, number 9 bar here, so half of 9/8 inch. All right. All right. Okay, so that is right. All right, so let's do a calculation, right? So now I call this C, and I don't call it CC because CC is clear cut, but I call CS, which is from the side. So 2-inch plus 3/8 plus 2 times 3/8 and plus a half of the 9/8. Come on, help me out. What do you have here? What do you have here, folks? What do you have here? What do you have here? I'm doing a hand. You have to beat me, right? What do you have? 3.69. Anybody? Confirm? Yes? Yes? Okay, good deal. 3.69 inch. Okay, that's from the side. All right, see? A lot of details. I tricked you. I did not tell you, right? Now you know. It's not that simple. You got to look through tables, right? You got to find out these numbers. I snatched it because I have experience. I'm empirical. I'm machine learning, right? I got an experience table in my head. You didn't yet. You got to accumulate yourself, right? Look into the table, help you there. Okay. All right. So that's how much of a distance I have. 3.69, right? And now how many bars I have? 2 bars. I got lucky, right? 2 bars only. So I'm gonna have another bar. And I know on the other hand side, it's going to be the same corner thing again. I already did that. All I need to do is find out the clear spacing between them two, right? What is the clear spacing between the 2 bars? What did we say last time? 1 inch, right? I said 1 inch, right? So you go with 1 inch. Can you though? Can you though? I don't know. Don't trust Bob too much, right? Because Bob likes to take shortcut. Right? I like the guessing. So let me tell you how to determine the spacing between the 2 bars. Okay, there are rules. So how to do that? Let me show you. Turns out this stuff is not that simple. We have to determine that before we come in to design stuff, right? Before we come into design stuff. Let me open up this. So I did not mention to you is that at the beginning, we said that there's going to be spacing requirements. What we didn't tell you is that take a look at this bar right here, the corner. Let's make a very complicated case. And I have a stirrups right here like this. I have 1 bar at the corner, 1 bar adjacent to it, and let's just say another bar floating on the top, okay? Floating on the top. This is not a precise drawing, but there are several parameters are precise. So in this arrangement, in this pattern, I need to determine the vertical spacing between the top row and the second row. And let me call it clear spacing vertical. Okay, clear spacing vertical. Okay, and now I also have to determine the spacing between the bars in the same row, and let's call it clear spacing horizontal. Okay, clear spacing horizontal. Okay, and in short, I'm just going to call it V. I'm just going to call it H. Okay, so in this case, CCH, CCV means vertical spacing is actually an equation, and that is larger of 1 inch, okay, and 4/3 aggregate diameter. 4/3 aggregate diameter. Okay. And CC, or actually, sorry again, I keep remembering wrong. So this CS, right? Clear spacing horizontal is actually a different set equation that is largest of bar diameter that being placed. In this case, you have so many different bar size, pick the biggest one, right? In this case, I call it dB. And then 1 inch. And then 4/3 D aggregate size. Right? These are the two equations from ACI telling you what is the requirement of the clear spacing, which I did not tell you last time. Okay. You say, Bob, you're cheating. You pick 1 inch from all these numbers. How do you know it's 1 inch? Well, let's play some game, right? Take a look at it. Am I cheating, right? So first of all, in our case, I order from Rala Ready Mix, and I know my pebble size, aggregate size is 3/4. Make sense to you? Not so small, right? 3/4, right? And what kind of spacing I need for vertical direction? You got to do calculations now, right? 4/3 multiply 3/4. That is what? 1 inch, right? Basic fraction, high school fraction, right? So 1 inch and 1 inch, what I end up with? 1 inch. There you go. For horizontal spacing, that is in lateral direction, right? Horizontal spacing, bar diameter. If I use number 8, if I use number 8 bar, what is it? If I use number 8, what is the bar diameter for number 8 bars? 1 inch, right? And this is 1 inch. And again, I call Rala Ready Mix. They have to give me 3/4 of aggregate size for no reason. And what I have? 1 inch again. So what I have in spacing? 1 inch. So that worked out pretty well last time when I say it's number 8 bars and it's 1 inch. But what bars we have this time? Number 9 bar. Can I use 1 inch anymore? Can I use 1 inch anymore? No, I cannot. Okay, I cannot. Be careful. Okay, so let's do the calculation. How many layers bar I have? 2 number 9, so 1 layer. So I don't have to worry about vertical spacing. I only have to worry about horizontal spacing. In this case, dB is number 9. What is the size of number 9 bars? 9/8. What is it? 1.125 inch. And aggregate size, let's say 3/4. So I had to tell you, right? Aggregate size 3/4 inch. But you end up with number 9 bar size. So the clear spacing is no longer 1 inch. Instead, it's 1.125 inch. Okay. Oops, right? New number. All right. So with that, let's take a look back, right? Let's take a look back. We're talking about 2 number 9 bars. Side 3.69 inch. And I need to find out the distance right here, which is another dB over 2. And if I do symmetric, right, half of B minimum. If I do half of B minimum, right, this is half of the clear spacing, right? So 1.125 inch divided by 2. So long story short, I'm going to write all down. So I say B minimum should equal to CS plus half of bar size plus half of the clear spacing in horizontal direction. And this is half B minimum, right? So CS 3.69 inch, let's see, yeah, plus dB, that is 9/8 multiplied by half, plus this is 1.125 inch divided by 2. And folks, what do I have here? Come on. What is it? 3.69 plus 9/8 multiplied by half and 1.125 divided by 2. What do I have? Bless you. What do I have? Punch in the number. Let's see what you have. Come on, come on. Larger, please. 4.815. 4.815. Very good. Now, this is only half of it. What is the full now? What is full now? Okay, that is what I have. Thank you. Okay, 9.63 inch. All right. So what is table A5? What is number from table A5? What is it? 8 inches. What do you have now? 9.63 inches. Which one will you use? The larger value. Okay, so shows you just now. If the beam is exterior condition exposed to weather and the concrete cover is different from that interior thing for table E5, cannot use table E5. Got to calculate yourself, right? And through the calculation, I got this weird number, 9.63. And what will you say if you're on the job site? Joe Schmo on the job site, what you say? 10 inch, round it up, round it up. Okay. Does that scare you? It sure scared me. Why? 2 Naminari bars, right? I got 10 inch of beam width. That means if I want to slip in 1 bar, that is literally impossible. Think of it, right? Right? I cannot slip even 1 bar more in 1 layer. Okay, so be careful what you're doing, right? It's not just a game, a lot of details in it, okay? And be careful. All right, so with this case, am I happy though? I'm pretty happy. Why? Because my width is what? What is my width? 12 inches. Fair and square. So I can put 2 bars in it, no problem. All right, but not all the case. All right, so I checked the minimum reinforcement area, good. I checked the bar spacing, and I can accommodate 2 number 9 bars. Am I done? Am I done? Am I done? Yes, I'm finally done for design. So last thing, okay? Last thing, let's be rigorous. Step 8, step 9. Okay, step 9, draw the section. Okay, and provide details. Most of you guys always forgot, right? So now I'm looking at the section and I have a 24 inch. I have a 12 inch. I know my concrete side cover from clear to side is 2 inch. And I have bars right here. Spacing here, as long as it's bigger than 1.125 inch, I'm okay, right? And outside here is 2 inches. And if I want to draw stirrups in it, I always can draw stirrups in it. And I can know exactly what is my location of my stirrups by showing the details here. Okay, by showing the details here. So, ladies and gentlemen, you are finally capable of designing a section with known geometry, but unknown reinforcement. Okay, and now you're officially ready to do your homework number 2. Okay, homework number 2 for design. Okay, all right. Okay. Okay, so it's not that easy, isn't it, folks? Right? It seems easy. The story is easy. I spent like 2 lectures talk about story, right? But the details are not easy. Gotta mind the details because everything is in the detail, like they say, right? Everything is in the details, like they say. Okay, so with that, we're done with design of a known section. Okay, we're not gonna meet on Thursday, but we're meeting next Monday, and we'll continue to talk about design for unknown section for singular reinforced beam. All right, thank you very much, and see you all next Monday. Okay, good luck on the career fair if you're going. Alicia, everything's okay?
Yeah, everything's good. Thank you.
Sorry for missing the early portion of it. I wasn't aware, just too much.
No, that's okay.
Yeah, well, ask me any question or email me, okay?
Okay, sounds good. Thank you.
Bye now, yeah.